Today we're going to be working on the process of predicting an organic molecule's NMR spectrum based off of its structure. The NMR spectrum is a chart that shows the environment that all the protons exist on in a molecule. That sounds complicated, but it's basically just a way of saying you can tell what a structure is going to look like based on each carbon's respective hydrogens are being treated, we could call it. That can be done by organizing the information into a table that has three different columns. The first column being shift. Shift is how much the proton happens to be deshielded, which can be affected by various things such as oxygens. The next thing is splitting, which is how many hydrogens belong to adjacent carbons. Then the last thing is integration, which is simply how many hydrogens are within that type. There are 5 different carbons or other molecules with hydrogens in this molecule, but there will only be 4 peaks because this and this are in the same chemical environment. So we'll begin and we'll move left to right on our peaks. The farthest left is this, which should have a fairly normal shift of around 1 and should be split only once because there's only 1 here, making it a doublet because the splitting is the number of adjacent hydrogens plus 1. This will move on and on and on, and that will give you a table that looks something like this. As you can see, these will have a high integration because there's a lot of them, and this will have a lot of splitting. This will have a lot of splitting because there are 8 hydrogens belonging to adjacent carbons. And this one will have a high shift because it belongs to an oxygen that's also attached to a carbon that has a lot of oxygen. This will be slightly farther down than both of these, and this will be slightly farther down than these because of the carbon double bonded to an oxygen, which will draw more electrons towards it. Now, using ChemDraw's function that allows us to predict NMR spectrum, what we can do is we can see that, oops, that was the wrong one. What we can do is we can see that we weren't too far off with our table. We have a large peak with a high integration right here, which corresponded to our first peak over here because there were a lot of protons that fell into this particular grouping. The next one is right here, and this is our highly split one, which belongs to this guy right here. This next one, because it was ever closer to this carbon double bonded to an oxygen, was a little bit farther down, and that belongs to this peak right here, as predicted. The final one has a very, very far shift because, as we said, it belongs to an oxygen. It's a very useful lab technique that I think is invaluable for anyone that wants to do any form of synthesis or purification.